Good evening, everyone. It's nice to see you all again virtually. Hope everyone's well and lockdown's treating you okay. It's a pretty strange time. I hope you've got a nice environment. That's always the hard one, is if you don't have a good place to settle and work. I know I work with a guy who's in a share house, and it's a little bit unpleasant for him when he has to do lockdown. So I hope you guys are in better situations. Had a little bit of housekeeping. Yoni asked me to let you know. I'll just share my screen again. Go to the course profile. So we're in week 2, unbelievably. It's gone very quickly. Sorry, just keep the chart outside. Yeah, so we're in week 2. Your homework is going to be due next week, was the thing, or a week and a half from now. So make sure you guys are on top of it. There's a practical this week, so practical here, but not next week. So I'm reminding you that. So review, start on the practical before you attend the practical session, because they're all online. So you get a bit of a heads up and you make more efficient use of the time when you get in. It's always a good idea. Okay, before you go to the Zoom practical, yeah. He also, if anybody is without a partner for the homework, please send Yoni an email so you're not waiting. I hope you're all getting together. It's all coming together there for you guys. That's housekeeping stuff. Cool. So I will go back to. Okay. What day is homework? So the question in the chat is, what day is homework due? Is I'm not exactly sure when the homework one is due, but I just know about a week and a half. Oh, you've got the date. Thank you. So 13th was the date that given in the chat. Awesome. Thanks, guys. Okay. Any questions before we start? Hopefully no computer gremlins today. I was up all night reformatting my hard drive and reinstalling Ubuntu, as I've thrashed it at work, and I made it crash in a bad state, and it was had a bit of corrupted hard drive. So hopefully that was what the problem was, and it's all fixed now. Not very good. Okay, so yeah, yesterday we finished unit 1, talked about factorial and did a bit about string parsing and playing around with JSON and HTTP requests, doing a simple sort of histogram of word frequencies. That's where we got to yesterday. And then we started on bubble sort. So I think I spent a little bit of time talking to myself when my computer crashed. So I might have dropped out in a couple of bits and pieces. So I want to reiterate, bubble sort. Sorting is a thing you always do in these sorts of CS type courses. It's not so much because sorting is a really super important problem. It is, but it's mainly thinking about algorithms and how you reason about performance, because it makes a big difference as a software engineer when you're working with software. That makes, like, I gave an example yesterday about integration and how integration scales with dimension, and it scales really poorly. It scales if you have a grid and you know, n points, and you're on m dimensions, it scales like n to the n, which is really bad. So getting that scaling under control is a big concern for lots of practical problems. And sorting is a good one to start with because it's easy to understand and it's good to go through. And so it's important. Like, you do use sorting is a thing you do all the time, but you tend to use the built-in one. So a lesson maybe is if you're using, you know, use the tools that are available to you. Don't reinvent the wheel. It's like a big problem. Like in software, they call it not invented here. If they'll have I guess it's a human factors thing of where if you're in an organization and you guys have come up with your own special thing, you'll tend to use that, even if it's objectively worse than something that's in the public domain that you could be using instead. So, you know, it's good to understand how these things work, know what's out there, and use the best thing. And if the best thing doesn't work, that's when you start having to be clever. Okay, so yeah, sorting, we talked about bubble sort. Bubble sort's this really simple algorithm. So you have an array, and we are going to edit it in place. This is this thing. So I made a bit of a fluff yesterday. I realized the example I coded really quickly was it actually doesn't work. After I think I was a bit flustered by the meeting. I was giving you, I sort of went on about, you know, this little exclamation mark means you're mutating the input. So the thing you get out isn't, you know, it's going to change what you've done. So when you return A, it will be different. This isn't, you have to be a little bit careful with the types in Julia. I'll just open VS Code. So I wrote an example off the cuff like this one above. I wrote a function pi. And so I was saying, this is just a convention. There's nothing about the Julia syntax that says you have to do this to say you're modifying something in place. I actually quickly wrote this example, and it actually doesn't do what I said it did, because it's for ints in particular. But if you do it for an array and you do something like this, where you're mutating the elements, it will change it. I'll just show you this. So we've got these two functions. So I talked a little bit about multiple dispatch, I'm not going to talk much about it. We had a question about how such and such a thing worked yesterday. I'm not going to talk too much about it. So I've given these types. So it's the same function, same name of argument, but depending on I've put a type annotation here. So if you want to say about which type of variable this will work for, you put these two little colons and say, so if X is an int, I'm going to do this one. If X is an array of type T, where T is a subtype of the reals, a little bit more syntax for you. So when you start doing a bit more in Julia, you'll start to do this stuff. So for anything, any type of number that's an array of numbers, I'll apply this function. That's what that bit of syntax means. I actually lied to you. So if I say X equals 2, so 2 is an int, so it's going to go through this version of pi. I'll get 4, but X doesn't change. So I actually lied. The example I gave was terrible because it doesn't actually do what I said. If I have an array of ones and I do this one, pi y, you see that y is mutated. So this is to do with the type of things. So we had a question yesterday about, can't remember who it was, but it was a fairly pressing question about, you know, types of variables and whether they're immutable or mutable. So the difference, immutable types you can't change. So this is actually a reassignment. So this is a new X when I do this one. So it won't change the X on the outside. Whereas, and you can check whether a thing you've got is mutable. There's a function is mutable in Julia. So is mutable X is false, is mutable Y is true. So this one will mutate Y. So I gave a terrible example. This one was bupkis. Please ignore that. But it just goes to show that accidentally, that putting this exclamation mark there is just a convention. It's a hint to someone else using your functions that this thing's going to do something that they might not expect, but it will only work on mutable types. So a little bit of a sidetrack. I just had that sinking sensation after I did the lecture that I said something wrong, so I should correct. But anyway, so bubble sort, A is a type of array. We're all good. So we're going to mutate array. We're going to mutate A. So we put this hint in there that we're doing some sort of in-place operation and we're going to change stuff. Cool. So sideways, but probably important. It will come back again. Later on, you'll do more of that stuff. You'll do a bit more when you're starting to construct your own structs and worry about mutable and immutable structs. So back to bubble sort. So what bubble sort do is we'll go through an array. If it finds an element that's in the wrong place, so it's bigger than the one before, the one after it. Sorry, if it's bigger than the one after it, it will switch their places. So this inner loop is like do one sweep through of this through the entire array, and go back into the next one and sweep through again, sweep through again, sweep through again. Keep sweeping through this. You'll notice that in this inner loop, I is not indexed at all. So it's just J's everywhere. So you just keep doing this sweep through the array, sweep through the array. Did a quick bit about timing. So I get said about software engineering tricks, use something like inbounds. Inbounds doesn't do bounds checking when it goes through this array. So if that's a problem for you, it'll slow down. And we see for a small array, there's a slight difference in performance, like 10% or 15%. Okay, so that's where we're up to. Okay, so we're going to actually go in through bubble sort a little bit more, in a little bit more detail today, and we'll see what's going on. So maybe this is obvious to you straight away, but it's important to go through this. This is important stuff. So got a little function here called do timing, and it has, this is one way you can initialize a vector of floats, undefined of length 0. So again, Julia syntax that, or you could have just done same thing, does the same thing. So just another version of doing that, initializing array. If you know the size, doing this is good, so you can put in the length. Okay, so we're going to go through this range of n. So every steps of 500 up to 10,000. We're going to randomly generate some data, randomly generate an array of ints of length n. We're going to use time nanoseconds. I think that's what it stands for. So get time in nanoseconds, perhaps every 5.8 years. Can anyone guess why it would wrap in 5.8 years? No one's brave. So think about how many, yeah, that's exactly it. That's exactly it. So how big, you could probably do this calculation in yourself. One of you can go off and do this in a Julia session yourself and go, how many nanoseconds are there in 5.8 years? And it is like 2 to the 64 or some suspicious number that's to do with the max number of uints or something that you'd expect to see. Hopefully that's what it is. Might be something else. I don't actually know, but I'm guessing it's that. So always on the lookout for these powers of 2, suspicious numbers to do with computers. So it'll be to do with the type it represents something. Yeah, it's a good answer, Alexander, in the chat. Okay, so get the time in nanoseconds, do this bubble sort algorithm on the data. Probably don't need the 1 to the end, that could be deleted. Then we get the time at the end, and we're going to push the difference in time, turn it from nanoseconds into milliseconds by dividing by 1,000,000. So yeah, push this into the time array and turn it into an int. Okay, and then you'll get an array of times and the range of values we estimated. So doing that, running this bubble sort thing, what we will see is we see something that looks suspiciously like a quadratic. So as we go from small, it starts going blah, blah, blah. There's this weird hump here. Again, as I can probably keep harping on, this abstract model of a computer is not quite what's going on. As you change size, different types of memory start to get used. That could be what's going on. It can be really difficult to work out what's going on here. But we also, this is pretty naive, this way of timing. As I said last one, if you want to be really careful, you use benchmark tools to time things. But this is just rough and ready, so you can see how it might work. So you probably want to do a few samples of this, get a statistical estimate rather than just doing one. Probably smooth it out a bit. It might change on your computer too, depending on how much memory you've got, what size caches you have, blah, blah, blah. So just eyeball though, it looks like it's quadratically with input size. So again, I was talking about integration last time, scaling to a power of n. This one's looking like a power of 2. This one, just really quick, I'm not going to say too much about it, but there's some packages that are useful for you guys. We'll talk more about data frames later on. Anyone in Pandas in Python, you're probably all familiar with that, I'm going to guess. Yeah, so Pandas, Python, data frames, and Julia. And this is a package for doing general linear models. So we're going to put the data into a data frame. So there's these 2 columns, just the range and the times. That's a pretty simple one. And we can fit a linear model with a formula that's like the coefficients of a polynomial. So there's an offset, some power of, sorry, something to the power, something to the time, some coefficient times x and some coefficient times x squared. We're not doing anything fancy like model selection to see what's going on here. It's just like, oh, it looks quadratic. Let's fit a quadratic and see what happens. Challenge question for anyone. Can you do it in linear algebra yourself rather than using this linear models package? Anyone have a go in background and try and work this out? If you get this data by running it yourself, you can have a go at trying to just do the least squares problem yourself with linear algebra rather than using this linear model package. Yeah, so this is just coefficients. So we've got some intercept to 0, which is good. If it's a 0-sized array, you'd expect it to hit 0. Some small negative on the first power and small number on the second power. It's a bit of fluff, so you can see the standard error on those, which you'd expect because it looks a bit noisy. And as a quadratic fit, it's fine. So it looks, it looks like it's doing okay. Again, not talking about model selection or anything fancy, just fit a quadratic. Does it look okay? Is residual small? Standard errors on the coefficient small? Okay, so we're going to use this as this quadratic trend we fitted to the data as a predictive model now at 30,000 and 50,000. So we're extrapolating well outside the range, and we'll see how well it does. Again, another exercise for you guys, if you want to show off, is get them estimated error at those points as well. See if you're within those, to see if you could do something like a chi-squared test to see if it actually is a good predictor. But this is just waving our hands and just, roughly does it look quadratic? Because we can do better than this anyway. We can do better than empirical. So we're going to predict the response and do the bubble sort, and we'll see what's going on. So, we're a little bit off, not too bad, but as you get further out, we predict 2.6, we get 3.4, not too bad. It's not great, but this is pretty rough. We've got lots of noise on the timings from the way we did the timing. We're only doing one sample. Could depend on what's happening on your computer at the same time even. If you have another process running, you'll get something different. There's a lot going on in a real computer. So yeah, so again, if that's not clear, these are the coefficients, there's the order, so x in this linear model, b1, b2. Try this yourself, see what coefficients you get on different computers, see if it actually looks quadratic. Hopefully it does. Lots going on in a real computer that's, it's not as deterministic as you'd like. Okay, just a little simple exercise here of like dividing by a power, and we see if we're on or off. Just another way of convincing ourselves whether power of 2 is whether this coefficient seems to be doing it. So we're just dividing the times by the rate, the size of that input array to the power of 2, and hopefully we get a flat line. So the power of 2 one, scaling like power of 2 seems okay, plus or minus, fluffy, but this one's growing, so it's definitely not 1.8. Throw another question out. What would be an alternative way of visualizing this? Anyone got any ideas? It's a thing engineers like to do. Boxplots, good idea. How about scaling, rather than dividing, maybe scaling the axes? What would be if you think it's got a polynomial trend, what would you do to the axes? Yeah, log plot. So you could plot it on a log axis and see if it's got a slope of 2 or a slope of 1. Another thing you could do, it's doing that anyway. So roughly, I hope you're semi-convinced that this looks like it's scaling to the power of 2. I'm pretty convinced. Yeah, so there's some constant. The limit as n goes to infinity, this thing goes to a constant, blah, blah, blah. There's some small term to the power that drops away. So little o notation in this case. So some error that decreases as n squared. So as n gets bigger, this term will dominate, and it should scale like that. So as a mathematician, you're probably more familiar with the little o. In computer science, they always talk about big O notation, so the order of an algorithm. Is this familiar to everyone or anyone? Anyone not seen it before? I guess it's probably a better question because we'll get less people saying I haven't seen it before. Yeah, so as I said, as always, there's a link to the Wikipedia. Natalie's seen it. Liam's seen it. Cool, that's good. Yeah, so it's this thing, big O notation. So there's lots of different types of denoting complexity. And so it's a way of representing how the complexity of the algorithm scales with the size of the problem. So like in the first lecture, I was talking about adding, with logic. So I did that adder circuit. So you could say, for a circuit, it's like the number of circuit elements is something like the complexity. Whereas for a serial algorithm, it's something like, how many times you do the computation, how does it scale? There's all these different types, depending if you get into the maths of computational complexity, there's all these things that do different things. I'm going to be really crude because I don't really know, all the different definitions. Some are like a lower bound, upper bound, probabilistic bounds, blah, blah, blah. Let's just be rough and just wave our hands and go like, oh, it's scaling like n squared, or it's scaling like some other thing. So yeah, so typically you'll find things, there's the big complexity classes are like order 1, so it's constant time. It doesn't depend on the size of the problem. You can have something that scales like log of the length, and you can have something that scales like the length, and then you can have something that scales like n log n, and then orders of different polynomials tend to be, different algorithms fall into those classes. So the worst are these ones that scale like order 2 to the n. So they scale like a factorial or something awful. A lot of really, really useful problems, and the exact solution to them is this horrible complexity class where it's exponential growth. I gave an example of one, like scale at that's why I was talking about the integration in multiple dimensions. It's like that scales very poorly with the number of dimensions. The prototypical examples of ones that scale very badly are something like the traveling salesman problem. Is that one that you're all familiar with? Natalie knows it. Anybody not know it? Let's see if I have to explain it or not. Okay, some people have done it. So it's simply, you've got a bunch of cities and you want to go visit every city once and come back to where you started and make the shortest path. So the best known algorithms are scale, like some power of n. So scale is the number of cities, goes big. So my day job is doing optimization on problems that are nearly always like this. So just doing magic tricks to try and reduce the order of these problems. You can think about like, lots of machine learning problems are actually like this, and all the tricks you use to get them to converge are tricks to reduce the complexity by sacrificing exactness. It's nearly what you always have to do. So ours anyway, blah, 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 waffle. Sometimes you get useful problems that are factorial. If you get famous if you work out how to reduce the order of one of these guys. If it was n to the 4 and you come up with a new algorithm that's down n to the 3, publish that, you're good. Yeah, there's useful algorithms that scale like n to the 6 that people use. I've done lots of ones n to the 3. Anyway, blah, blah, blah. So why exactly is bubble sort order n squared? Is this obvious to anyone or not obvious? Probably is obvious if you've thought it through. So this implementation is n squared. I hinted yesterday, there's a test you can do that reduces it to n, order n. And that was to have an early bail. When you're going through this it depends on the data. So there's like a best case complexity for this one. If you put in a check that, is it already sorted? Did I ever actually hit this statement? Like, did it ever happen? If it never happens, I can bail after one run. So you just have to do this test once through. So it's really about the number of comparisons taking place. So we have two loops. We've got this outside loop, inner loop, and then do a bunch of stuff. So we're doing a test of size. Is this thing bigger than this one? We're doing some memory addressing, and then we're writing the results back into the place. So all those computations are happening all the time. So the outer loop runs n-1 times. So if you count it up, blah, 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 down to 1, you can get this sum. And that should give you this. So half n squared n on 2, which in terms of what's the dominant term, n squared. Oh, sorry. It is 2. That's terrible. Thank you, Len. Yeah, so basically just turning the crank. You just go, we're going to say, or blob all this stuff into one thing and go, that's the compute bit. This bit's fast. The expensive bit we're doing this many times if we just count it up. So in this code, we're just going to do some dirty logging where we have this, just a counter. How many times does this counter get hit? We're not actually, it's going to be proportional to this because like each of these operations, so like accessing this memory element, doing this comparison, and then assigning these things all have a different time. So lump them all together, there's some coefficient of how many times this thing gets run. You can do all these operations that many times. If you do the profile and you plot it for a small data set, we're going to get 28. I'll leave it for you guys to check. You know, you can verify yourself that you're always going to do 28. So that calculation is correct. It's pretty straightforward. That's pretty easy. It's like you've got an inner loop and an outer loop. You're going over the array. You're going to do it this many times. Pretty straightforward. So this one's more just probably a hint, wink, wink, for assignment. You could do a different sort with a difference. So this is just sideways. You can modify this one to take a comparison function. So in terms of syntax again, so semicolon, you know, this is a required argument for this function, and these are optional arguments with a default. So in this function, there's a named argument called comp for comparison, I'm guessing. The author was guessing they want to put a comparison function in it. Remember that this guy is a function. So, you know, if you want help, just go into your thing, it's a function. Again, it's like plus where, you want to use it that way, but you can actually use it this way. It looks weird. So, you know, this one will take an optional comparison function that you could do something different with if you wanted to call it. If you wanted to do something exotic, you could define your own function, pass it in, and so we could change it from less than to greater than. You could sort on the sum of digits. So we've got an inline function here where it's summing the digits. So again, these are the arguments, num1, num2. It's a 2-argument thing. We're going to go digits num1 is greater than sum of digits num2. So if you want to do some exotic stuff. Also, again, this one is useful, is an anonymous function. So this is just this syntax again. I think I talked about this last time. You could also do it this way rather than naming it and passing it in. So this up here, it's gone mycomp. I'll give it a named function. You don't care. It's kind of like you do these anonymous functions when they're sort of disposable. If I'm never going to use this thing again outside the scope of this bubble sort, like why would I bother naming it? I'll just pass in this anonymous function representation. So anonymous because it doesn't have a name, like literally in Latin what it means. Or Greek, whichever one it is. No name. so you're just giving the arguments mapped to this sort of syntax of going like, I'm going to sum the digits. So you can do it instead. You could call this thing with mycomp, or you could just pass an anonymous function, or you could make an incredibly exotic thing. So here's another exotic one that's kind of bad because it's got a global. You get this internal shudder as a software developer when people put globals in, because they end up doing long range strange things, and yeah, avoid them if you can. There's another way you could do this. I won't talk about that because it'll be a little bit confusing, but okay, so yeah, you say K, we're going to call this thing a global. We'll put it in a begin end syntax. So you can make a little function. You can make a multi-line anonymous function this way. You can have more going on here. So it's doing like this profiling one before. It's got this global K that's going to get incremented, and yeah, you can see that it will do something. It'll do it based on the sum of the digits. So hopefully that's clear. That's a bit of an aside. Again, it scales to the square. Any questions so far before I go on? Everyone seems happy. Deafening silence. It's good, I guess. I've got this paranoia that I'm talking to myself again after yesterday. So, good to see some interaction. Okay, so now your built-in plot is heaps faster, over 200 times at this time. That was back up at the start. Sorry, scrolling around. Right back at the start, we were doing some comparisons. So the built-in sort, this guy's running in 0.1 of a second. This guy's 0.0005 of a second-ish. So for a 10,000 size array, it's way better. Way better. So probably not software engineering tricks if you're getting that much of a difference. It's not going to be some clever representation. It's more likely to be a clever algorithm. 200 times faster at 10,000, it probably only gets worse. And yeah, unless there's special case for bubble sort where you can bail in ordering if it's already sorted, but that's sort of a silly case. Okay, yeah, not because of built-in performance improvement. Different algorithm. So this is the difference, different algorithm. So how are you guys going on the homework? Have you guys had a play with the Goldback primes question? Is everyone having fun with that or not? Or is that a horror show? Challenge, not so well. This algorithmic thinking, how can you flip the problem around to do less work? It's like always what you think, the way you have to think. Like if you have to do something twice or multiple times, it's going to scale really badly. So I don't know if I said this yesterday, but Andy and I got competitive over this and he beat me. So his record for the Goldback primes up to 1 million, he's got it in under a second. He's got it in about 600 milliseconds. So that's a benchmark for you guys. I think you get a really good grade if you beat that. Maybe not, but thinking about how you can flip the problem around. We both had to cheat to get that fast. So mine's about half his speed, so he's winning. Yeah, so thinking about what could you do differently? So like if you're doing something repetitive, maybe you can do it a different way. Maybe you can flip the problem around so you don't have to do things more than once. So if you keep searching back over the same array, maybe that's not a great idea. That's just a hint. So yeah, think about how you can flip the problem around. It's nearly always the way. So like if you keep scanning over the same thing again and again and again, it's like you're probably doing something wrong. There's probably a way of reformulating the problem that will make it better. So Wikipedia sorting thing, you can see the sorting zoo. I had a question yesterday about different sorting algorithms. So here's, lots and lots of things. So we got best case complexity, average case complexity, and worst case complexity. So as I was saying with bubble sort, if you have this early bail, hopefully I'm not lying, bubble sort will be in this list somewhere. I can't find it. Bubble sort, so order n. So like you just scan through and go, oh, it's sorted. That's the best case. I don't have to actually do anything. You can always just stick that out the front of any other algorithm though, and you can make it the same. So it's not a great reason to use bubble sort. Like I said, bubble sort's an educational example. Don't use it for real. Average case complexity n squared, worst case complexity n squared. So depending on the algorithm, you can get different performance guarantees. So these guys tend to be the ones, and I said about timsort, that one's used in a lot of programming languages as a default. I'm pretty sure it is in Python, maybe in some code paths in Julia. I'm not sure. I have to go and have a look. Some implementation of quicksort and merge sort tends to be the one. You also got this memory complexity. So we didn't talk about that. So memory complexity, if you're doing it in place, there's nothing. There's no cost to that. Merge sort and quicksort there is. Can do an in-place version of it sometimes. So lots of different, you can go through the zoo of sorting things and see if you can understand them, but just to get an idea of how this is scaling. So this does not look quadratic to me. This is running the built-in Julia sort through this same algorithm. So notice the sorting times, less than a millisecond, whereas when we're doing it up here, we were getting up to nearly 100 milliseconds. 100 times faster, at least, that size, the small arrays. So it looks like it's scaling like linearly, but it's not actually. If you go through the same, we just talked about it, it's actually got this n log n complexity. So there's a logarithmic term, so it grows a little bit faster than linear. And there's heaps that have n log n complexity. The reason, and you can prove, so exercise for reader, you can go off and prove that you can't do better than n log n in terms of number and comparisons, unless there's something funny about the data. If something about, this is just depending on how you set the problem up, your real world problem may not have the same characteristics. If, stupid example, say they're all ones, they all have exactly the same value. Of course you can do better than n log n. You don't have to do anything. It's already sorted all the time, always. But if you know something about the statistics of your data, this isn't true in general. But the general version of it is you can't do better than n log n for number of comparisons. So we're going to look at later on heap sort, because this is going to come back again and again in this course. A heap is a data structure. Data structure is, we had this question at the end of another good question yesterday about trading memory for speed. So can you lay out the data? So rather than, so we're using an array here, always we're inputting an array of values. Could we have something better than an array that will burn a bit of memory but make the computations quicker? There's that, and there's algorithmic tricks about flipping stuff around. So heap sort, because we're going to use this heap data structure. So actually, in my day job, again, I use a heap all the time for a thing called a priority queue. So we do simulations of physical processes. So actually businesses, we make little statistical models of businesses, and we fit machine learning functions to some data. We have some functions that are deterministic, and we put them all together as a bunch of, say, business transactions that are going out into the future. That's what we do at Alara, where I work and where Andy works. So inside this heap data structure is really useful because we want to do events in an order, and heap is a data structure which is really useful for doing something called a priority queue. So again, heap sort's not the best algorithm necessarily for doing sorting, but it's useful because we're going to have this heap data structure. So I'll bang on a little bit more about a heap later on. Yeah, so we can actually see, I think, linked. So again, Julia is open source. You can actually find, go into master base, Julia GitHub repo. Talked a bit about Julia. You can actually go to the repo. Instead of downloading the binaries, if you're a masochist, you could clone this and build it yourself. Don't do that. But you can go and look at, a lot of Julia is implemented in Julia itself. So a lot of these built-in functions will be implemented in Julia. And you can go through and look at what they actually do. So if you want a hint about how, how to do something, you can go and see what some very, very clever people have done. And okay, where are we going? So there's something in here like quicksort. Yeah. Anyway, you can go through. I won't, or you're just trying to navigate around, but you can have a look yourself. So these things look a lot like quicksort. Again, they're using this inbounds macro to check, so they don't do bounds checking, so that will make it a little bit faster. And again, looks a little bit arcane, but that looks like the quicksort. So yeah. Okay, so any questions there? So that's a hint about how Julia's one works, a hint about where you can go look up an implementation of a sorting algorithm in a language that's been optimized. So as I said before, optimized code isn't always the friendliest code to go and have a look at. It'll be, yeah, that's it. So any questions so far, or I'll go on a little bit more. So we're talking about a heap. We're going to start on data structures, a few simple ones, and I'll just talk about that till the end of, we'll go through a little bit of this. So any questions before I go on about sorting? Everything clear? Does white space in your code affect timing at all? No. So like I said, yeah, someone asked me that yesterday about indents and stuff. It's like, no, just let's all get stripped. Yeah, there's like normal standards for readability. So you try and make it look nice for other people to read. It's like I was saying in the first lecture, code's read more than it's written in when you're actually using it for real. So making it look nice is important. But yeah, when the way Julia does its just-in-time compiling, it will have a parser that's going over this expressions and stripping out white space and just getting the interesting bit. That's when it's doing that. What you see when you look at that at code lowered is the first step in that process. I shouldn't care. So basically, arithmetic operations, data access, they're the two things that kill you. So you just sort of count up how many times you do that. So if you're thinking about how you might make something faster, access stuff as little as possible. Do as little as you can. If you can reuse a result, reuse it. The worst things are allocating memory in programming for speed. The things that will really, if you have to resize an array or some data structure, make it bigger and bigger and bigger, that will kill performance really quickly. In Julia in particular, a thing called type instability will be the thing that slows you down sometimes, but you probably won't get that with simple stuff you're doing now. We'll give you a hint about how to do performance tuning in Julia later on. It's a bit more, it's actually kind of a fun game to hunt through code and make it fast. Okay, we'll start talking about data structures. What is a data structure? This might be a bit naff, but don't confuse a data structure with a database. They're very different things. A database is like data with a data structure, if you want to think about it that way, as a way of indexing quickly. And ensuring a bunch of stuff happens that, when you're writing, when you've got multiple people writing to a file, they don't tread on each other's toes. Okay, so an array is like the basic data structure. So you've got random access to any point. So we've had this one again and again and again. We can get, you get the thing about an array is you can index into a point and you get the data. So I said about this one, so lookups into an array are constant time. So doesn't really, looking up is really fast. Like that's, computers are good at that stuff. Other operations can be worse. So this is, so I got a question, is @show the same as print? No, again, so always go to Julia documentation if you want to know. So @show is kind of useless. It's just show a result. You can look up show. It will give you far more details than you want about what show's doing. Same with print. These print can take an IO string is the big difference. It defaults to something called standard out. But you can actually put it into a buffer, put it into a file. Lots of details. I'd say go off and look in the documentation, but it shows just a nice way of plotting stuff out. You can use a print one, whatever you want. Shows just a convenience thing for dealing with this stuff. So we've got data. So useful thing is Ltype. So if you have a useful function, another one to introduce to you guys. So determine the types of elements generated by iterating a collection of a given value type. For dictionary types, Ltype. So not dictionaries, but for an array, what Ltype will do is tell you the elementary type of the data. So it's an int64 in this case. So if we had something else, it's float 64. So that's the thing. So knowing the type of the data, you can, in Julia, you can have arrays of type any as well. Don't worry about that now. Oh. Sorry, it's going up there. Oh no, sorry, I'm copying the wrong thing. Size of. Sorry, ignore that. I was copying in the show bit. So size of says your size in memory, and this thing is a pointer. Does anyone, if people have done C programming, so lower level programming, would know about pointers? Is this going to be a new thing for most of you or not? They can be annoying. Yes, they can be annoying. Pointers can be very much annoying. It's new. So what this is doing, so again, everything, I just say it every time because I'm dumb. It's like, so it's telling you about the native address of an array or string, obviously in a given location index. So this is not a thing you should be doing in Julia. You can have this, no, not prescriptive. You can do whatever you want when you're programming, have fun. But it's not like normal to do this. You can do some stuff that's a bit wonky if you do it. So what it's actually doing is pointing to an address in memory. So you get this thing out. It's a hex string, blah, 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 blah. This is an address in memory. So somewhere on your computer, it's going like the value for this data is over there. So you can get where it's stored. So again, so we can get the index. So pointer at the start of the data. And what you should see, so it's different from the one in here, but what you should see is that these are 8 apart. And so for the sec, because each of these elements are 8 big. So I skip over like that. When you do a data structures course, there's lots of books you can read. Everything in memory will have an address. That was the reason for everyone going to, sorry, Liam's, so is everything on your computer on an address like that? Everything in memory has an address. That was the reason everyone, maybe you guys aren't old enough but everyone used to use 32-bit operating systems, and then they went to 64-bit because you couldn't address enough memory. Exercise again, like how big is 2 to the 32? It's like 4 gig of RAM. If you have more than 4 gig of RAM, you can't address it in one cycle. You need to burn cycles to go to somewhere else. So everyone went to 64, and we're never going to have that much RAM. Seems to have been true. Yeah, so 32-bit OS, you have a maximum memory size you can address quickly. Yeah, so read up about, so classic data structures, there's these few things, linked lists, queues, and stacks. Yeah, you won't do this. We don't do this thoroughly. There's this course, I don't know if you guys know it, where you can do a bit more. There's lots of books and you can read up about this if you're interested. Just this idea, I'll quickly go on to multi-dimensional arrays because this stuff is interesting. I'll just start on this. Yeah, so again, pointers are a kind of weird thing. So if you're using another language where you don't have a thing called garbage collection, you'll have to do some of this memory management yourself. That's the advantage of using a language like Julia where it has garbage collection. It will tidy up after you. Don't have memory leaks like you do in C. Okay, so multi-dimensional arrays. So we've just talked about straight arrays, but you can also make this thing. So this is knowingly called a matrix of uint8s. So we've got two sizes, n and m, and you can make a matrix. We could make this 100, reshape it, whichever way you want. We're doing int8s, so the Ltype of an int8. So if you did the size of that, it'll be smaller than this 8-bit one. So you should see these are just jumping up one at a time. So the interesting thing here is if you look at where this memory address is, it's as it iterates through this array. So a thing you can do, yeah, sorry, let me just show you this. This is the size is a useful thing to use. So if I have an array, a equals 1, 5, you can go length of a will be 5. If I have this matrix, I'll make it small. If I go length of data, it's 15, which is the number of elements of this matrix. If I do otherwise, if I do size, I get 3, 5. So you can actually iterate through data. You can just index it with this thing called a Cartesian index. You can see where this element is in memory. And if we go through this thing, the natural thing is to go like it's next to each other. It's next to each other in memory. It's laid out in memory. So there has to be a choice about how this matrix is laid out in memory. So there's actually an iteration order that it goes through, you know, because you're just going 1 to n pointer at this index. It will go through in a particular way. So programmers, when they're making, when developers are inventing a programming language, they choose a way they're going to lay out matrices in memory, and you've got two options. You can go, well, you've got more than two options, but the two obvious ones are going down this way or across this way. So column major or row major is what they call it. So we can see the iteration order in Julia. IJ is just like this, so that's that linear index into this thing. That's not clear. If I give it a single element, 1, 2, 3. So let's see. 1, 2. So it's actually going from 80 to 7 to 53. So the way it's actually, you can give it 2 coordinates. You can go 1, 2. So it's going through these ones first. So that was a choice for Julia, I think most languages. So are matrix representations in multidimensional arrays while linear algebra is so useful in CS? Yes, that's one reason. I'd say a different way of thinking about it is that linear algebra is like the most powerful tool of humanity. It's like it's like the best thing we've come up with. So if you can map your problem into linear algebra, you have many, many, many tools to help you with problems. So like sideways thing of like a lot of my work's to do with graph theory and turning graphs into linear algebra representation and then doing linear algebra tricks on graphs is like super powerful. But okay, and we've got a course, Math 3204. I don't know, I'm not familiar with that one, but yeah, applications of linear algebra to anything is good. Like linear algebra to quantum mechanics is powerful. It's a universal tool. So this one, I'll just talk about it really quickly. This is actually a misleading example, but you notice that these guys are close together in memory if you're going this way through the array, and they're far apart in memory if you're striding through this way in the array. So it's actually, this is one of these things where low-level details are coming up to the surface in Julia, is that the way you iterate through an array will change the speed. If you iterate this way through the array, it will typically be quicker. Typically be quicker than if you iterate across this way because things are closer in memory. This depends on the size of the array. If you actually, the canny amongst you will have a look at this one, and you will notice that, so what we're doing is I use the Ltype for the data. So we've got time going through the array, striding through this way first, and then we flip the order of these guys. So we go J slowest. So in this guy, we're going I slowest, J quickest. So we're going through the array in that direction in the first one, and then that direction in the second one. These timings are flipped around, which is kind of annoying if you look at this one. But the reason for this is to do with the size of the array. I'll see if I can reproduce this here. Oh, I don't have random input. Yeah, so it's slower that way, but you'll notice that this matrix is really out of square. So if we change this, go NM, let's make it more square. And we do this guy again. Blind test. So it's faster second time now. Oh no, that's still the same. So this one's, we're sort of lying. Oh, did I generate data with the wrong size? No, that's interesting. So something about, it's actually a bit of a puzzle. I spent too long thinking about this, but it should be that it's back to front, it's striding through with J varying the quickest. So yeah, it's sort of back to front to what you'd expect with this example. So even though, you know, computers are complicated, how memory access happens is complicated. Even though you have this mental model, they should be exactly the same. Like if you're just thinking about, oh, they're constant time, doesn't really matter about which way you iterate through the array. You know, it should be exactly the same which way you iterate through. It's kind of weird that it makes a difference. And it's kind of back to front that the memory access pattern in this case is not what you'd expect. It should be quicker going through one way, and it's not, which is interesting. So open question for you guys, work out what's going on. But again, practical stuff, like it shouldn't matter which way you go through the array in general. Particular details of implementation and hardware mean that you do get a difference depending on which way you iterate through the array. I'll leave it there. Any questions on that stuff tonight, guys? Oh, thank you, guys. I'll see you guys in a week, I guess.